All right. Okay. So last week we mentioned that for linear time-invariant systems, you will be able to completely characterize them using the channel impulse response, using the unit impulse response. Okay, and this is because for any signal, you can write it as a superposition of unit impulses, and therefore the output of the signal would then be the superposition of the response of these unit impulses. Okay, so once you are able to obtain the unit impulse response, you will be able to characterize completely the input and output of a linear time-invariant system. So because of this, this tells us that various properties of linear time-invariant systems should also be reflected in the form of the unit impulse response. Okay, so we started to go through a few properties, starting from the memoryless property. Okay, so last time we mentioned that if a system is memoryless, which means that its output can only depend on its input at the same time, this implies that the channel impulse, the unit impulse response should be non-zero only at time 0, which means that the impulse response should be equal to a delta function, this unit impulse, up to some scale k. Okay? Right, so if a system is memoryless, then its impulse response is just a delta function, a scaled delta function. All right? Now, we also looked at the case of invertibility. Now, we showed that if a system with impulse response h of t is invertible, this means that you will be able to find another impulse response h sub 1 of t such that the convolution between h of t and h sub 1 of t will be equal to a delta, a unit impulse or a delta function. Okay? And if you recall, this unit impulse is exactly the impulse response for an identity system. So this means that if you cascade a system with response h of t with a system with impulse response h sub 1 of t, then the effective system will be an identity system. Okay? All right, so we've gone through memoryless property, invertibility. So what comes up next is causality. Okay? Now, if you recall, what does it mean for a system to be causal? Okay, so what does it mean for a system to be causal? So we say that a system is causal if its output depends only on the present and past values. Okay? Only on the present and past values. So we know that the input-output relation of a LTI system can be written in this form, right? So the output is equal to the convolution between x and h, right? Or you can write it as the convolutional sum of x of k times h of n minus k. Now, if the output depends only on the present and past values, this means that the summation can actually go up to only n. Right? Because for a causal system, it can only depend on x of k for k that is on or before time n. Right? So for a causal system, the output at time n can only depend on the input at time n or before. Right? So for this, saying that this summation goes up to only n implies that h of n minus k must be 0 for all k greater than n, right? Or in other words, h is 0 for all time instants that are negative. Okay. So a system is causal if its impulse response is 0 for all negative time. Okay. So intuitively, what this means is that if you have a system that is causal, and you insert a unit impulse at time 0, you insert a impulse at time 0, then the response to the impulse must be 0 for all n less than 0. So your response must look something like this. Your response, h of n, sorry, my computer is not responding very well. Okay, so our response will look something like this, right? Something that is non-zero only for n greater than 0, but 0 in the negative axis. Okay? So if you insert a unit impulse at time 0, the response will be non-zero only for n that is greater or equal to 0. For all n less than 0, the response is 0. Okay? So this is quite intuitive, right? Because for a causal system, you would not expect to get any signal, to get any response before the signal occurs, right? So by the definition of a causal system, the response can occur only after the signal has arrived, right? Okay. So a system is causal if it satisfies this condition. Okay. Now this holds similarly in the continuous case. So for a continuous time LTI system, it is causal. Okay. It is causal if this convolution here can integrate only up to time t, right? Because if you integrate beyond time t, this would mean that the output at time t depends on some x after time t, okay? And this cannot be the case if the system is causal, okay? And this implies that the impulse response should be 0 for all negative time, right? So this is the condition for continuous time, okay? So we can look at a few simple examples. So for example, if the impulse response is equal to a unit step function, you see that a unit step function is only non-negative in the positive axis. So therefore, the system should be causal, okay? Now, another example, suppose that Hn is equal to delta n minus delta n minus 1, right? This is a sample at time 0 and a sample at time 1, okay? So again, because h of n is 0 for all n less than 0, therefore this system is also causal, okay? So both of these systems are causal. Okay. Now you can also look at examples in continuous time. So for example, you can take h of t equal to delta of t minus t naught, okay? Now is this system causal or not? Okay. So how many of you think that this system is causal? You raise your hand. And how many of you think it's non-causal? 没有人举手是怎样？啊？你说 T naught， 就是对呀，所以你认为应该怎么样？对对对 ，Yeah, you're right. So if T naught is positive, then this is causal, but if T naught is negative, it is non-causal. Okay, thank you. Greater or equal to 0. Okay, and it is non-causal otherwise. Okay. Now, how about h of t equal to u of t minus t naught? Okay. So this is a unit step signal rising at time t naught. Okay. So similar to the above, this signal is this system is causal if t naught is greater or equal to 0 and non-causal otherwise, right? Because if t naught is greater or equal to 0, you would have non-zero values only after t naught. Okay, so this is the same here. So the next property is stability. Okay, so we've gone through memoryless, invertibility, causality, and the next is stability. So we say that a system, recall that we say that a system is stable if every bounded input produces a bounded output. Okay, so a system is stable if a bounded input produces a bounded output, right? This is the bounded input, bounded output stability. So for, in this case, right, we can show that it is sufficient for an impulse response to be absolutely summable. Okay, so if you want a system to be stable, it is sufficient for its impulse response to be absolutely summable, meaning that the sum of the absolute value of the impulse response must be finite, okay, must be less than infinity. Okay. Now we can show this, right? So suppose we start out with a bounded input signal. Okay, so let us consider an input signal xn that is bounded by some value b for all n. Okay. Now, for a system to check if a system is stable or not, we need to check if the corresponding output is also bounded. So we look at the output, the absolute value of the output, which is equal to the absolute value of the convolutional sum hk x n minus k for k from minus infinity to infinity. Okay? Now this can be upper bounded by the summation of the absolute value of these terms inside. Okay? So I can bound this by the sum of the absolute value of hk times the absolute value of x n minus k. Okay? Now, by the premise of the proof, we know that this x of n minus k must be less than b. Okay? So I can further bound this by b times the summation of the absolute sum of h. Okay, and this holds for all n. Okay? Now, if this sum is finite, right? If this sum is less than infinity, then yn will be bounded for all n. Okay? So therefore, we have shown that if the impulse response is absolutely summable, then the system is stable. So hence, then yn is bounded and thus the system is stable. Okay? Okay. So here we have shown that it is sufficient, okay, for a system to be stable. It is sufficient for the impulse response to be absolutely summable. Okay. Now, you can also show, right, that it is not only sufficient, but it's actually necessary as well, which means that if you have an impulse response that is absolutely summable, then the system must be stable. Okay? So we're not going to show that here, but you can find it in one of the problem sets. Okay? So this absolutely having an impulse response that is absolutely summable is also a necessary condition for stability. Okay? And for this, see problem 2.49. Okay? Okay. So this is the proof for the discrete time case. But you can prove the same result for the continuous time case as well, following almost the exact same procedure. Okay? All right. So similarly in continuous time, right, if you want to show this, you start out by taking a signal that is bounded for all t, and then the output y of t, which is the absolute of the output, which is the absolute of the integral of h of tau x of t minus tau d tau. Okay. Is less or equal to the integral of the absolute value of the function inside. Okay. So the integral of the absolute of h times the absolute of x d tau. Okay? And again, since this x is bounded, therefore we can further upper bound y of t as b times the integral of h of tau d tau. Okay? So similar to before, you will have a stable system, or you will have an output that is also bounded if this integral here is finite. Okay? And this integral here is called, the absolute integral of the impulse response h. Okay? So if this is finite, meaning that the impulse response is absolutely integrable, then you also have a stable system in continuous time. Okay. Now here we look at a couple of examples. All right, so in the first example, we have an input-output relation given by this. So here y of t is equal to x of t minus t naught. Right, so this is simply a delay system. Okay. Now what is the impulse response for this system? Okay. So the impulse response is the response to an impulse. Okay. So the impulse response is what you get if you take x as delta of t. Okay. So in that case, h of t is equal to delta of t minus t naught. Now we can check if the system is stable or not by taking the absolute integral of h of t. Okay. So substituting h of t inside, we get the integral of delta of t minus t naught dt. Now I'm neglecting the absolute sign because delta is always non-negative. And when you integrate over a impulse function, the integral is just equal to 1, right? The area of an impulse is always 1, right? And because 1 is finite, this implies that the corresponding system is stable. Okay? Now, suppose we look at this other system here, where the impulse response is equal to a unit step function. Okay? So to check if this is stable or not, we take the absolute sum, okay, which is equal to the sum of u of n. Okay? And this because the unit step function, right, is equal to 1 from time 0 up to infinity. So if you sum over the unit step function, the sum is unbounded, right? So this sums to infinity, which implies that the system is unstable. Okay? What we want to talk about here is, just a side note about using the unit step response to represent the system instead of a unit impulse response. Okay, so previously, right, through our previous discussions, we have shown that a linear time-invariant system can be uniquely characterized by its unit impulse response. Okay, but actually, this is not the only way to characterize a linear time-invariant system. So sometimes it may be more convenient to use instead the so-called unit step response. Okay, let's call it Sn or S of t for continuous time, which is basically the response to a unit step function at the input. Okay. So let us define S as the unit step response, which is this response to a unit step function at the input. Okay? Now, in this case, what would be Sn? Okay, so in this case, Sn would be, right, taking the input, taking un as the input, and convolving it with the impulse response Hn. Okay? And this is equal to the summation of hk u of n minus k for k from minus infinity to infinity. Okay? Now, u is non-zero only when k is less or equal to n, right? So u is non-zero only when k is less or equal to n. So this limits the summation from k equal to minus infinity up to time n of h of k times 1, which we can omit here. So from this derivation, we can see that the unit step response, right, the response to a unit step function at the input is just the sum of the unit impulse response from minus infinity to time n. So given the unit step response, you can actually compute the unit impulse response by taking Sn minus Sn minus 1. Okay? So this shows you that, this is saying that, if you say that a linear time invariant system can be completely characterized by H, then this means that you can also completely characterize the system with S. Because given S, you will be able to compute H, and then that will help you characterize the system. Okay? Now, having H equal to Sn minus Sn minus 1 is also straightforward if you view it from the superposition property of a linear time invariant system, right? Because if you take instead delta n as the input, then delta n we know we can write as un minus 1. Okay? All right, we know that a delta, unit impulse, is equal to un minus 1. So by the superposition property, the response to delta, which is h, should be the response to u minus the response to un minus 1. Okay? And this holds for continuous time as well. All right, so in continuous time, your st, you can show is just h of tau d tau integrated from minus infinity up to time t. And you can actually recover the impulse response h of t by simply taking the derivative of the unit step response. Okay? Or you can write it like this. Okay? So the main takeaway message here is that, in addition to the unit impulse response, an LTI system can also be characterized by its unit step response.